instruments are calibrated in radians, Charlie, but there's nowhere to go.
I know, Ed. Every direction looks the same. Our star charts are no good. And there's all these weird-looking pulses flying around.
In the last program, we looked at another unit for measuring angles, the radian. We saw that 2 pi radians equals 360 degrees, and pi radians equals 180 degrees. If we want to measure angles in radians, we make a simple calculation. 1 degree is pi over 180 radians. 30 degrees, then, would be pi over 6 radians. We know that pi is about 3.14, but we usually don't approximate these expressions. It's not difficult to work with pi. We just carry it around as a factor. 60 degrees equals pi over 3 radians. And 90 degrees is pi over 2 radians. Now, we want to graph a trigonometric function on the Cartesian plane. The simplest one is y equals sine x. By the way, this doesn't mean that y equals sine times angle x. It means that y equals the sine. Here's a to insert their sine values. A calculator tells us that the sine of 0 degrees is 0. The sine of 30 degrees is 0.5. Sine 60 is 0.87. And 90 degrees, 1. Let's put the angles on the x-axis of our plane and the sine values on the y-axis. Now we can plot y equals sine x. When the angle is 0, the sine value is 0. When the angle is 30 degrees, the sine value is 0.5. Sine 60 is 0.87. Sine 90 is 1. Sine 120 is also 0.87. 150 is 0.5. And 180 is back down to 0. If we continue with angles up to 360 degrees, we find negative values in the table, and these points fall below the x-axis. Now let's connect the points. This is a sine curve or sine wave. It's described by the equation y equals sine x. A sine wave has a relationship with a unit circle. The terminal arm of an angle is 1 unit in length. As the terminal arm lifts and the angle increases, the sine value, opposite over hypotenuse, also increases. As the terminal arm falls, the opposite side gets shorter and shorter until it's 0. As we raise the terminal arm again, we can plot the growing sine ratio. The hypotenuse is a radius, and so will always be 1. At 60 degrees, the length of the opposite side is now 0.87. So the sine of 60 is 0.87. At 90 degrees, a special point is reached. Here, the opposite side and the hypotenuse are the same length, and the sine value is 1. This is the maximum value for the curve y equals sine x. After we pass 90 degrees, the opposite side starts to get smaller again, and the curve drops. At 135 degrees, the sine ratio is 0.71. At 180 degrees, we're back at 0. Now, the opposite side becomes negative as it passes into the third quadrant. At 225, the ratio is minus 0.71. At 270, we reach minus 1, and at 360, 0. If we keep rotating the terminal arm, creating angles greater than 360, we would produce an extension to the sine wave that is actually a repeat of the first cycle. We've graphed y equals sine x using degrees. Let's try radians. We'll have to mark the x-axis in radians. We know that 360 degrees equals 2 pi radians. And 180 degrees is pi radians. 90 degrees is pi over 2 radians. Let's try one we haven't looked at. 270 degrees. We know it's halfway between pi and 2 pi radians. It's 1 1/2 pi, or 3 pi over 2. Now it's simply a matter of establishing a table, using radians instead of degrees, plotting some points, and drawing the curve. We can also plot a curve for negative values of x. This part of the graph lies to the left of the y-axis. The sine wave is called periodic because the wave repeats at equal intervals. In this case, every 2 pi radians. We should mention the graphing technique we use to sketch these curves. For instance, when we look at the table of y equals sine x, we find that the maximum value of plus 1 occurs at pi over 2. And the minimum value of minus 1 at 3 pi over 2. Similarly, we find the points where the curve crosses the x-axis. And finally, we can sketch in the curve itself.
Geez, Charlie, some of these pulses are getting pretty close.
Yeah, Ed, they sure make a lot of noise when they go by, too.